All right. So earlier we had looked at what happens when you apply the Euler method, the forward Euler method, to a stiff problem. And as we saw, it's like that resulted in very restrictive time step restrictions in order to maintain the stability properties of the system. So it's worth mentioning, of course, that not every numerical method suffers from those issues. So let's look at what happens when you have the trapezoidal rule applied to a stiff system. Okay, so if you recall, it's like a trapezoidal rule looks like the following. Yn plus 1 is equal to yn plus h over 2, f evaluated at yn tn plus f evaluated at yn plus 1 tn plus 1. Okay, and the model problem which we're looking at has the form y prime is equal to lambda y, right? So this is applied to y prime is equal to lambda y. Okay, so let's see what happens. So this says that yn plus 1 is equal to yn plus h over 2, right? Lambda yn plus lambda yn plus 1. So I can take the yn plus 1 term to the left and then end up solving for yn plus 1 in terms of yn. And so let's see what happens. So you have the identity minus h over 2 lambda times yn plus 1 is equal to the identity plus h over 2 lambda yn. Okay, so that says that yn plus 1 looks like the following. 1 identity plus h over 2 lambda over identity minus h over 2 lambda, the whole thing times yn. Okay, so it's easy to convince yourself again that this means that yn looks like the matrix, again, identity plus h over 2 lambda divided by identity minus h over 2 lambda to the nth power applied to yn. Okay, and you might ask, well, what do I really mean? It's like by this sort of quotient, and you'll see that this is a polynomial, if you will. It's like in a matrix lambda, both in the numerator and denominator. So, so what I really mean here is that I multiply this matrix by the inverse of the denominator, and because basically this is a polynomial in lambda, these two things commute with each other, so it doesn't matter whether I'm multiplying this matrix by the inverse of the denominator on the left or right. Okay, but in general you have to be a little bit careful. Okay, so all right, but that's really more or less what I mean. Okay, and then what you can show then is that this solution, as a consequence of this, what happens is that you have yn plus 1, well, actually, let me rephrase that, yn, right, looks like the following expression. It looks like, 1 minus 50h over 1 plus 50h. And if you recall, that has to do with the fact that lambda had eigenvalues minus 100 and minus 1/10, right? Okay, so so what you basically do again is that you, sorry, this is y0. What you basically do is that you write down the initial condition y0. It's like in some linear combination of eigenvectors, and then formally speaking, the numerical solution behaves in such a way that the two terms involving the eigen sort of directions don't really speak to each other, okay, at least formally speaking. So you get this 1 minus 50h over 1 plus 50h to the nth power times x1, and then you have another term which is 1 minus 1 over 20h divided by 1 plus 1 over 20h to the nth power times x2, where again x1 and x2 correspond, where are basically eigenvalues or multiples of eigenvalues of the multiples of the eigenvectors. It's like corresponding to the minus 100 and the minus 1/10 eigenvalues. Okay. All right. So as before, it's like what you basically need is that the things inside the parentheses have to be sort of less than 1 in absolute value. Okay. So you can check what that means. So you have the condition of 1 minus 50h over 1 plus 50h in absolute value is less than 1. And you also have a condition that 1 minus 1 over 20h divided over 1 plus 1 over 20h is less than 1. Okay. All right. So we can. So let's look at this one. So this means that 1 minus 50h in absolute value is less than 1 over. So 1 plus 50h in absolute value. Okay. And you can check that this is true for all values of h which are greater than 0. So this is true for all h greater than 0. And the same thing is here. This is true for all h greater than 0. So basically, what you see is that if you're concerned about this issue of stability, which is to say that you want a numerical solution which doesn't sort of explode when the continuous solution is actually decaying, right? With the usual Ford-Euler method, there was this very, very severe time step restriction. But with the trapezoidal rule, even though you've applied it to the same stiff problem, it's like which gave the Euler method a great deal of grief, with the trapezoidal rule, there is no restrictive time step restriction. Okay, so what this is again meant to illustrate is that just because you have a stiff problem doesn't necessarily mean it is beyond sort of the purview, it's like of a numerical method. You just have to choose the right numerical method. Okay, and what we'll see basically is that this notion of a right numerical method has to do with something about this idea of being having very mild or non-existent restrictions. It's like on the time step, irrespective of the eigenvalues of the linear operator, if you will. So we'll see it's like how to sort of state that in more precise terms, sort of just in a little bit. All right.